Hi, and welcome to Module 6 of an Introduction to Engineering Mechanics. Today's learning objective is to calculate the forces acting on systems of particles, or multi-body problems. This is a typical multi-body problem. This is an example from a textbook by Drs. Dave McGill and Wilton King. Although I said in this Coursera course there was no required textbook, I am going to use several figures and examples from a textbook called Engineering Mechanics, Statics by Drs. McGill and King. And I will I'll put a little note on below those figures to show when I'm using those. But I know Drs. McGill and King, and they were kind enough to allow me permission to use material from their textbooks in this course. Both of those gentlemen are professors emeritus at Georgia Tech, and so it's great that they're supporting this Coursera course. Okay, so here's the situation. We have this person who is exerting a force in this rope and holding up these systems of pulleys where there's a weight which would be known, weight 1 here on the right, and then a weight 2 here, which is greater than weight 1. And so if we go over here to a model, got a model of this situation. So I'd be the giant person, if you will, over here on the left-hand side that's holding this cable as it's attached and holding this system up of the two weights. So let's go back over here and look at the assumptions that we would make in solving this problem. Typically for these problems, we make several simplifying assumptions, these pulley problems, to help us to getting a simple but a fairly accurate solution. If we find that these assumptions are not good and we need more accurate answers, we may need to go back and relook and include some of these forces and things that we're neglecting. So one of them is that we assume that there's frictionless bearings in these problems. We assume that there's a constant tension throughout the cable or the belt or the rope, and we neglect the pulley weights. And so let's look at these assumptions again over here on my model. And so again, if I'm the man here, the giant person over here on the left, I'm holding this cable, and we're saying that or this string, if you will, and we're saying that the tension in this string is the same throughout, over to here, and the tension in this string or cable is the same throughout. We're assuming that these bearings are frictionless, okay? And we're also neglecting the pulley weights. We're saying that the pulley weights are much insignificant when compared to the weights themselves. And so those are some good assumptions to simplify the problem and still give us a fairly accurate answer. So in solving this problem, we take our system, which has to be completely in static equilibrium, and we apply the equations of equilibrium. And we talked about these last module. We must have a balance of forces in the x direction and a balance of forces in the y direction. And so let me draw my x and y directions here. Let's call to the left x and to the y up. And so this whole system has to be in equilibrium, and each piece of the system must be in equilibrium to satisfy static equilibrium. And so what I'm going to do is I'm going to separate this thing out, and I'm going to look at just one little piece here. I'm going to look at this pulley, P1, and I'm going to draw a free body diagram of that pulley. So this is a free body diagram of pulley 1, or pulley P1, if you will. And so I separate that pulley from the rest of the world here, and so I'm drawing it unconstrained. Here's the center. And now I apply the external forces that are acting on that pulley. And so I see that on the right-hand side here, I have this chain, if you will. And so if I cut that chain, there's a tension in that chain which is equal to the weight 1. And that's going to be pulling down on the right-hand side of this pulley. So I've got W1 here. One of our simplifying assumptions was that the tension in that cable is the same throughout, and so if I cut it over on this left-hand side and apply a force reaction there, I get W1 down. I have this connection of the center of the pulley to the ceiling, And so I have to cut that, and there'd be tension in that. I'll call that tension 3. And then I have a tension in this other cable, which is coming down from the center of the pulley. And if I cut that tension I'll call T2. And I want you to note on T2 that if I follow the tension in T2 all the way around here, that it's actually the tension or the force that the person must exert to hold the system in equilibrium. So let's make a note of that. We'll note that T2 is the force the person exerts. So that's going to be our answer. So now we apply our equations of equilibrium. As I mentioned, here they are on the right. We've done them in last module. We don't have any forces in the x direction in this problem, so we don't have to worry about this first equation of equilibrium. So we'll just sum forces in the y direction, and we'll make sure they're balanced, so we'll set them equal to 0. I have to choose a sign convention for assembling my equation. This is arbitrary, and I'll show you that it doesn't matter when we do this. So what I'll do to start here is I'll just choose up as being positive. And so when I assemble my equation, I have T3 is up, so that's going to be positive. And then I have weight 1 is down, so that's going to be negative in accordance with my sign convention. T2 is down, so that's negative. And the weight 1 on the other side is down, so it's negative. And all that has to equal 0. And so I end up with T3 equals 2W1 plus T2. And so that's my equation that results from that force balance. Just to show you that it wouldn't have mattered if I had chosen my sign convention as being down arbitrarily, let's just redo that. So I have sum of the forces and the y equals 0. I'll choose down as being positive. And I would get, well, in this case, T3 is up, so it would be negative, minus T3. W sub 1 is down, so that's positive in accordance with this sign convention. So that's plus W1. T2 is down, so that's plus T2. W1 is down, so that's plus W1 equals 0. And you'll note that if I carry T3 to the other side, add the T1s to, or W1s together, that these two equations are exactly the same. And so you get the same result regardless of the sign convention that you've arbitrarily chose to assemble the equation. Okay, so the equation that results, though, we have a problem here because we have how many equations? Well, we have one equation. And let's count the number of unknowns. Well, we would know W1. We'd know that weight given in the problem. But we don't know tension T2, which is what we want to find. That's the force the person exerts. And we don't know tension T3. So we have one equation, two unknowns. And so we have an unhappy face. And so what do we do next? And you may want to think about this for a second and then come back. Try to think about what we would do next. Okay, once you've thought about that, what you need to do in this case is, okay, every piece of this system has to be an equal. Let's take another piece and draw another free body diagram. So we're going to try another free body diagram. And the one I'll choose next is pulley P2. So at the top here, I've written my analysis from pulley P1. I arrived at the equation T3 equals T2W1 plus T2, so two equations, or one equation, two unknowns. Now let's do a free body diagram of pulley P2. And in fact, I'd like you to take a few minutes on your own and draw that free body diagram and then come back and we'll do it together. Okay, now that you've completed that, here's my body, pulley P2. Here's the center. I apply my external forces. I have, this was T2 on pulley 1 in tension, so it was pulling down on pulley 1. It's going to be pulling up on pulley 2. tension in that cable is the same throughout, so it's also, if I cut it on this left-hand side, it's going to pull up on the left-hand side, T2. In the middle here, if I cut this chain, remember the tension in this chain was the same throughout, and it was equal to W1, so that's up, W1. And then finally, I have the tension in this rope, which is hooked to weight 2, and so that's going to be down, and that's weight 2. So that's a good free body diagram. That's what you should have arrived at. Once we've got that, we can assemble our equation. Again, there's no forces in the x, so we'll only sum forces in the y direction, set it equal to 0. I'll choose up as being positive. And so I've got T2 positive because it's up, plus W sub 1 positive because it's up, plus T2 minus W2 equals 0. And if I solve for T2 now, I get T2 equals W2 minus W1 over 2. And so that's my answer. So if I'm given the values for the weight 1 and weight 2, I subtract the 2 and divide by 2. That's going to give me the force that the person must exert. And you'll notice that I get a bonus in this, that I can actually go up here and put the result for T2 into this equation and find out what T3 is.